So what is uniform circular motion? This is motion where an object moves along a circular path, but it moves with a constant speed. The only thing that's changing is the direction of the object's motion. But because velocity includes both speed and direction, there is an acceleration associated with this. There is a change to the velocity, it's just not a change in speed. And the direction of that acceleration always points inward towards the center of the object's motion. And therefore the net force must also point in that direction. And the term toward the center there's a Greek term for that called centripetal. And so that is why sometimes this is referred to as centripetal motion with centripetal force and centripetal acceleration. Sounds very specialized, but it turns out that there are many situations where motion does follow this constant speed along a circle pattern, or it comes very close to it. And so it is a worthwhile discussion. A lot of times, though, when people think about this, they sense an outward force. They think back to a situation where they've been moving along a curve or moving in a circle, and they can recall an outward push. Do recall that with accelerations, we always do feel the exact opposite of what is being done to us. And so when a car accelerates forward, we feel like we're getting pushed backwards. And so in the same way, if we are being moved around a circle, we feel as though we're getting pushed outward, when in fact we're being pushed inward. So to this question, is there an outward force on this ball? Well, in a word, no. If the string were to break, that ball would not move outward, it would move tangent to the path. And that can really help us understand how this works. We're going to take a look at a video. The full video is at the address that's listed here if you wanted to see it. But we're going to look at a clip of a video where a ball is being kind of moved around in a circle within this hoop. And look what happens when the hoop is lifted. Notice how the ball moves in a straight line, and it moves tangent to the circle at the point when it was released. So look very carefully here. That has the ball leaves. Okay, so it's now moving in a straight line. It doesn't arc outward, it doesn't move outward. There's no outward motion whatsoever. The reason why this ball was going in a circle was entirely because of the inward push of that hoop on the ball. As soon as that inward push was released, the ball moves along at a constant linear path. So that's very important for us to understand, that the forces and the accelerations on this sort of an object are inward at all times. You know, it's though true, again, as I said, that our experiences do confuse us. You know, if we're sitting in a car and that car is moving around a curve, it certainly feels like we're getting pushed outward, pushed in this case to the right, as we're in that car. Again, I want to stress that in order for you to turn towards the left, there is going to have to be a force pointing in that general direction, pointing towards the center for that to occur. There is an outward force, but that's your force on the door. So, you know, in the act of pushing on something, you do sort of experience that, and so you do seem to think that there's this force, but that force, again, is on a different object. We will need to focus on the object that actually is moving along that circular path, and that net force is always going to have to be toward the center. When we calculate centripetal acceleration, that value of acceleration depends on a couple of things. It depends on the speed of the object and the radius of the curve. So, you know, again, picture yourself in a car going around a circle. If you travel faster, then that's going to require a greater acceleration because your speed is faster. It's going to be harder to, for that force to cause a change in that direction. Also, if the radius is smaller, making a tighter curve, a quicker turn, that's also harder to do. That requires a greater acceleration, and therefore it would require a greater force. So, things to kind of keep in mind as to why this formula for centripetal acceleration makes sense. Of course, the force will also depend on mass, and we will be using F equals ma in these problems. There's a second video if you'd like to watch it. It's linked off the website, and it will show a few examples of how these ideas are incorporated.